All right, ladies and gentlemen, welcome back to Patterns of Inheritance. This is the third installment of this. So if you missed the first two installments, please either go back to Google Classroom or go back to my YouTube page and see what you have missed. Starting off with a little bit of review. We talked about dominance and recessiveness. What this means is there are two alleles for each trait, right? Each aspect of your body, you actually are going to have two genes that we call alleles, one from mom, one from dad, and one may be more dominant than the other, meaning your body is going to listen to this allele over the other one. And it doesn't matter which parent gives it to you, all right? I always have some people think that dad is always more dominant than mom or something like that, and that gender has nothing to do with that unless it's specifically on your gender chromosomes, your sex chromosomes, and we will get to that in a little bit. Right? Otherwise, has nothing to do with that at all. Right? It's just some genes, some alleles are more dominant than others. Right? And the dominant one is the one that's going to show up in the phenotype. Right? Is going to show up on your body. The recessive one won't. The recessive one doesn't want to be seen. Right? So, if you end up with a recessive trait showing, that means that's the only one you have. Mom and dad both gave you a recessive trait. Like red hair, for an example, is a recessive trait. The only way you can have red hair if mom and dad both gave you red hair. It's the only way it shows up. Here's something I don't think I covered in the other installments. The fact that recessiveness can skip generations, right? First off, I want to say that that is very misleading. Genes do not actually skip generations, all right? You cannot get anything directly from your grandparents, right? It just looks like it does because it's a recessive trait. It doesn't show up in your parents' bodies, right? But they still had it in them. You got it from them. How that works is like this, all right? We got two families up here, right? Family 1 and family 2, all right? And their kids are going to get together and have kids. So these are going to be technically the grandkids. So we're going to call these people up here grandparents, grandpa and grandma, and grandpa and grandma. All right, so grandpa is what we call homozygous dominant, meaning homozygous means they're both the same, dominant because they're both dominants, all right? Homozygous dominant. Grandma is homozygous recessive, and she has the recessive trait. And the only way to have a recessive trait is to be homozygous recessive. The only way to show it. I didn't pick a trait. Let's go with eye color, I guess is good. All right, so grandpa has brown eyes, grandma has blue eyes. Blue is recessive. And the other family, exactly the same. Grandpa has brown eyes, and he's homozygous dominant. Grandma has blue eyes, making her homozygous recessive. Right? And when they get together, not really much choice in the matter here. You know, grandpa is going to pass on a dominant B, grandma's going to pass on a recessive B. And that's going to happen each time because that's all they have to give. In this family, exactly the same thing, right? Grandpa passes on the dominant Bs, grandma passes on the recessive Bs. And the resulting offspring are now a mix, right? They're not homozygous. They're what we call heterozygous. Hetero means different. So heterozygous, they each have different alleles. And when this individual will get together with this individual, now instead of two homozygous people getting together, we have two heterozygous people getting together. So here's what we got to look at, right? See what we're looking at right now. This heterozygous person has a dominant brown eye and a recessive blue eye allele. Dominant wins, so this person has brown eyes. Same thing over here with mom. She has a brown eye allele and a blue eye allele. Brown eye is dominant, brown eye wins, so she has brown eyes. That doesn't change the fact that the blue eye allele still exists hidden in their genetic code, and they could still pass that on. And it really is, for each parent, a 50-50 chance. Flip a coin. They have two alleles. Which one are they going to pass on? Heads dominant, tails it's recessive, right? If it happens to be dad's dominant and mom's dominant, the kid is homozygous dominant. If it's mom's dominant and dad's recessive, the kid is heterozygous. If it's dad's dominant and mom's recessive, again, heterozygous. But here's what we're here to talk about. If dad passes on his recessive and mom passes on her recessive, that's two recessives. That means a brown-eyed person got together with another brown-eyed person and they had a blue-eyed kid. That's a 25% chance, 1 out of 4 chance that these two heterozygous brown-eyed people could have a blue-eyed kid. This kid's going to grow up going, I have blue eyes. Neither of my parents have blue eyes. Oh, I must have gotten it from my grandma. It looks like it skipped a generation. Right? Now we know it doesn't actually skip. We just call it that because that's what it looks like. Right? Important fact, only recessive alleles do this. All right? You can only skip generations with recessive phenotypes. Right? Dominant will never skip generations. That's an important fact for you to remember for later in this video. So I'll say it again. Recessive skips. Dominant does not skip. Recessive skips. All right, moving on. I said a little something about sex-linked traits. This is the only one that matters whether you're male or female. Right? These are the traits that are attached to the X and Y chromosomes. I talked about that in the last video. So I'm assuming that you understand what's going on with this. These are going to affect men and women differently. For instance, anything on the Y chromosome will only affect men because women don't have Y chromosomes. Only men do. If it's on the X chromosome, it could affect both people, men and women, because everyone has X chromosomes. But still going to be a little different because men only have 1, women have 2, and that's going to matter. So take a look here. Example is hemophilia. Hemophilia is a genetic disorder. It's a mutation. The ability to make a scab for your blood to clot is on the X chromosome. If the genes involved in that are mutated somehow, you may not be able to make those scabs. That's what hemophilia is, the inability to make a scab. So if you get cut, you just keep bleeding and bleeding and bleeding. You may even have to get a blood transfusion to save your life. Like that big of a deal here. And this problem is on the X chromosome. Oh, I'm a little too far. Let me back up here. So looking at over here, I made this red to show that it has the mutation, and I made this red to show that it has mutation, and this one does not. That matters, right? Because if one X is affected for the man, well, he now has hemophilia, right? The only X he has is mutated, and that's all he has to work with. So he is a hemophiliac. However, one X for a woman does not make her a hemophiliac because she still has this good X telling her how to make scabs. So she can scab, she won't bleed to death, she's fine. However, she is still what we call a carrier, right? Meaning she still has the mutation, it's just not bothering her. But she's going to pass one of these on when she has a kid, and again, flip a coin. Heads this one, tails is this one. We don't know what's going to be until it happens. So she could pass on that mutation, and her kid could be hemophiliac. Now, she could still become a she won't, but it's possible for a woman to be a hemophiliac if both of the X's. If her mom gave her a mutated X and her dad gave her a mutated X, then she would be a hemophiliac. Not very common at all for a woman to have hemophilia. Right? Same rules apply for another example I gave in the past. Color blindness works the same way. It's also a sex-linked trait on the X chromosome. So it's very rare for women to be colorblind, very rare for women to be hemophiliacs, but it is possible. All right, passing on traits. So here's how this works. That's how it's going to happen. The alleles are going to pair up. Dad over here, just like everyone else, has 2 chromosomes for every trait, and mom has 2 chromosomes for every trait, for every aspect of her body, right? I should say genes for traits, chromosomes are many genes. So many genes, many alleles. Right? And they're going to have a kid. Now, I don't know which one of these is going to pass on to the kid, but one of them will. And if it's the Y chromosome, then this person is going to be male, XY. And I still, well, now I know, but before I did that, I didn't know if it was going to be the pink X or the green X from mom. But in this case, it passed on her pink X. If she passed on the green X, he would probably have different traits and look different because your chromosomes, your alleles tell you what to look like. So half of each pair from each parent is going to be passed on to make a new pair. And this is going to allow for variation. You know, it could have been the red X and they could have had a daughter. It could have been this green X and they could have had a daughter over here that looked different. Oh, sorry, Y. Could have been this X and this Y and be a different looking male. So all different combinations. But there's another way we make things different too. We learned this next one in the last chapter. Sometimes the chromosomes go through something called recombination, what we called crossing over last chapter, meaning this pink X and this green X might combine a little bit. They might mix with each other, and this pink X can get a little bit of the green, and they can end up having a kid that looks a lot like this one, but slightly different because of that little bit of green information. This will increase the variation. This is why so many people look different across the world, because we have all these different ways of combining. So, important thing. All right, now here's the meat of today's lessons. This is what everything building up to, the pedigree. Right. This is a vocab word, so we've talked about it before. A pedigree is basically a family tree. Really, that's it. It's a family tree. It is a chart that shows a relationship within a family. Except the pedigree goes one step further. It's a family tree that shows a genetic trait. Only one trait you pick. I don't care which one. And when you get your family tree, you're going to pick your trait and check out everyone in your family and think and find out who has this trait. If they have it, you bubble them in. Just fill it in. Right? So in this family tree, whatever trait you're talking about, I don't care what trait. Let's say very loose earwax. Why not? That's one I haven't used in a while. Very loose earwax. So it turns out grandma has very loose earwax. Grandpa has very solid earwax. So we're going to bubble grandma in, fill her in because she has it. None of their kids have it, but they are able to pass it on. Uh-oh. Skipping a generation. I guess loose earwax is a recessive trait because this kid also has it, so we fill him in. And this kid has it, so we fill her in. And yes, him and her. Shapes matter on this. It can be used to show who is, like we just saw, who is carrying the recessive gene, the recessive allele. Kind of an important thing because, as we just saw in a previous slide, certain genetic issues might be recessive. So how does it all work here? Let me backtrack, show this again. We got a bunch of shapes, squares and circles, and we have a bunch of lines, horizontal lines and vertical lines. Right? Those are the things that are important here. So let's find out what those things mean. A square means you're looking at a male. Right? All males in your family are going to be shown as squares. And if that male, that person has the trait that you're looking for, you fill them in. Right? That is a person who is showing the trait. Right? We're not saying what their genotype is. We're not saying that they're carrying the trait hidden in the recessive allele. We are saying that this physically shows up on their body in the phenotype. And if they don't have it, you don't fill it in. You leave them white, leave them blank. Women, same thing except you're a circle. Right? All women are shown as circles. And if they have the trait, you fill it in. If they don't have the trait, you leave it blank, you leave it alone. In this case, I'm leaving her filled in, right? This gentleman does not have whatever trait we're talking about. This lady does. Now we have those lines, horizontal lines and vertical lines. Horizontal lines connecting the two mean that they are a mating pair. This man and this woman are together and they are reproducing together. Right? Vertical lines, let me get some more room here. Yeah. Vertical lines and brackets, I'll show you a bracket in a second, are going to be children. Right? So these two got together, they're a mating pair, and then they have a son together. Well, they've been married for a little while, so they're going to have a couple kids probably. So when you have more than one kid, you make a bracket. So here's the vertical line, and then the rest of this is a bracket showing that they are all the kids connected to this vertical line. So this couple And this woman has the trait we're looking at. I don't know, we'll say red hair. So this woman has red hair, and they have 3 kids, a daughter and 2 sons, and this son also has red hair. All right, time goes on, these kids grow up and they get married. And by the way, they don't actually have to get married. The horizontal line just means you're mating. Biology doesn't care if you're married or not. So this guy grows up and has a partner, and they have kids, and also passes on the red hair to one of the 3 sons. This woman gets a partner. They have 2 kids, and oh, look at that. Look at this. The woman does not have the trait, neither does this gentleman, but they still manage to pass it down. So that means this woman got the trait from her mother as a recessive trait, but showed the dominant trait from her dad. But she still had the recessive trait hidden in there, and she still passed it on to her kid. And this kid, in order to be recessive, has to have 2 recessive traits. So he got the other one from his dad. Both of these people passed on a recessive to this guy. Right? That's how that works. And I said, who cares about red hair? This could have been a genetic disorder instead, right? Maybe talking about passing on hemophilia or passing on some sickle cell anemia, something dangerous, right? It's important to keep track of these things. So here's another family. It's a different family, not the same one, right? 2 males over here, 2 females over here. Oops. 3 males, 2 males and females. So this is a different family. And we're going to show carriers now. Just like before, that couple were carriers. They had the trait from the parents, they just weren't using it. So how do you find out? How do you know if someone is a carrier? Right, well, one way is, there's 2 ways to do it. One way is look at the parents. So I want to know whether or not this person is a carrier. Right, well, I look at his mom, and his mom has it. He does not. All right, that doesn't mean anything yet. You know, for all we know, this person could have a dominant trait but passed on the recessive, and a recessive trait, or this could be recessive and pass on recessive. So we don't know yet. But if we look at this guy's kid, now we see a skip generation. We see a pattern here. This person has it, her son does not, but he still passed it on to his son. So it skipped a generation. And remember what we said earlier. I told you to remember this. Recessive traits can skip, dominant traits cannot. So we know that this is a recessive trait. This person passed it on, so this person must be carrying it. We show a carrier by filling it in half, all right? And you would do this yourself. Right? No one's going to give you a pedigree filled in with half shapes. Now, if you got a pedigree off someone, it would look like this. And you would take your pen or pencil and you would fill in the people you figured out are carriers. You do that yourself. Take a look over here, same deal. This person does not have the trait, but her daughter does. So, again, skipping generations. Oh, I forgot about that one. I'll talk about why that one is in a second. They don't have kids for us to know. So, they skip the generation. So now that we know for a fact that this is a recessive trait, well, what do we know about recessives? Yeah. In order to show a recessive, you have to be homozygous recessive. So this person has to have 2 lowercase letters. Let's see if I can draw here. Give me a second. That's not what I wanted. Text. All right, so this person will say, we said red hair. So red hair, so lowercase h for hair. My mouse disappeared on me.
12 seconds later.
All right, I'm gonna have to edit this out.
2 hours later.
All right, guys. Sorry about technical difficulties. I am back. But anyway, what we were talking about, we were trying to figure out uh, who is a carrier. So here's what we do know. We do know it skipped generations. So this person is a carrier and this person is a carrier. So how do we know that this person is a carrier? They don't have kids to skip generations. Well, because we've already figured out that this person is recessive. An only way to be recessive is to have two recessive alleles, which means they don't have anything else to pass on. They only have recessive, and recessive. So they passed on a recessive. That's it. We know that they're not fully shown. Like we know he didn't pass on a recessive too because he would be fully colored in when we got this pedigree. Right? So he was left blank. So we know he doesn't show the trait, but we know mom had to have passed it on to him. So he's carrying. That's one way of figuring it out, by looking at the parents and looking down and following the patterns. I said there were two ways to figure this out. The second way is starting at the bottom and working your way up. We know that this person has the traits, but neither of the parents do. So again, skipping generations. So we know it's recessive. That's not what we're looking to see. We want to see who's a carrier. Well, if this person's recessive, it means they have two traits. You got one from dad. Where did they get the other one from? That's right, mom. So mom also had the recessive to pass on. So mom is also a carrier. Same deal over here. This person is recessive. So that means they have two recessive traits. Got one from mom. So had to get the other one from dad. So in that case, dad is also a carrier. So everyone in this generation is going to be a carrier in this particular family. Another family might be different, with a different setup. Now, here's the question. Are these two carriers? Quite frankly, we don't know. Same thing over here. Is this person a carrier? We don't know. It's possible that both parents passed on the dominant traits and homozygous dominant. We won't know until later on when this pedigree keeps going and these kids grow up and they have their own kids. So a pedigree is never finished. So as we said, the trait in this pedigree is recessive because dominant traits do not have carriers. If it were dominant, then the parents of affected children would also express it, right? If you have a dominant trait and your kid has a dominant trait, you both show dominant traits. But you don't always show your recessive one. All right, moving away from pedigrees. And a lot of people usually get confused by them, so if you have any questions, feel free to contact me during my office hours. But for now, I'm moving on to selective breeding. This will be really short. This is the easy thing here. Selective breeding is choosing which organism to breed and attempting to get a desired offspring. What that means is it's kind of like natural selection, where in nature, the ones with the best traits to survive do survive. And if you're alive, you pass on your genes, right? That's natural selection. Selective breeding is kind of like that, except we, the humans, are choosing, right? So if you have a dog breed, right? I want to make money selling dogs. I'm going to select who I'm going to breed. I'm going to choose based on who I think has the best traits. Right? I'm going to get a male dog with what I think are the best traits and a female dog who I think has the best traits. In which case, I would go back and use one of these pedigrees, which good, reputable dog breeders use these pedigrees, and I would see who has the good traits that I'm looking for and see whether or not they're dominant or recessive. Because if they're dominant, I got a pretty good chance of getting puppies with it. Recessive might skip a generation. I may not want to gamble that. So I would use that pedigree and select which animals to breed, which traits that I want. Another example would be horses. And this one they do all the time, really easy. simply by winning races. Whoever wins the race is clearly the fastest horse, or the best horse for racing at least. And then if I own that horse, I could sell it off, or at least sell the sperm for a much larger amount of money than other horse owners. So people are coming to me and selecting my horse to breed with their horse. And hopefully they get baby horses that will grow up to also be very fast and they can make a lot of money selling. That's selective breeding. Get 2 fast horses and hope the offspring will also be fast. Another example, when I already said with dogs, golden retrievers. Turns out golden retrievers have a very desirable trait. They're great with children. They are one of the top family dogs. So I would use a pedigree and find out which dog comes from a long line of other very friendly dogs. And yes, obedience and calmness and being good with families are genetic traits. Some behaviors are genetic. So I would find out which animals had those traits, come from a family with those traits, and breed it with another dog who also has a good pedigree that have all those traits on it. Meaning I have a very high likelihood of getting a litter of puppies with those really good family traits. So I get 2 golden retrievers, and I know that my puppy will also be a really good golden retriever. That's how you actually made dog breeds to begin with. Remember, dogs, their ancient ancestors were wolves. You know, Humans created dogs by selectively breeding. Exactly the way I said, they chose the wolves that had the best temperaments and bred them. And then out of those litters, picked the ones with the best temperaments and bred them. And just kept doing it over and over and over again until we had domesticated dogs who just have really good family friendly temperaments. And then, of course, all the other various dog breeds were based on what we wanted. Some people wanted to breed animals that were really small so they can fit on your lap. Other ones wanted to breed them very big so they can protect the house. And that's how you get all the different breeds. All right, ladies and gentlemen, that is it for patterns of inheritance. Right? That is the end of the notes. So, as I said before, if anything you don't understand, feel free to email me or get a hold of me during my office hours. Email me anytime, but I will be waiting at my laptop between, actually, I don't want to say the times because they could possibly change, but look at Google Classroom for the current times that I would be available sitting at my laptop. All right, have a good day and keep an eye out for work associated with these notes. See you guys.